Hello everyone, my name is Viraj and today we'll be looking at the 14th problem from the CP-31 sheet by TLE Eliminators under the 1000 rated questions. Let's go. So moved on to my sheet over here, ticked off 1000 and I'll go to my 14th problem, shoe shuffling. Okay, let's read this. A class of students got bored wearing the same pair of shoes every day. So they decided to shuffle their shoes among themselves. In this problem, a pair of shoes is inseparable and is considered as a single object. Now there are n students in the class and you have been given an array S in non-decreasing order where Si is the shoe size of the ith student. A shuffling of shoe is valid only if no student gets their own shoes and if every student gets shoes of size greater than equal to their size. You have to output a permutation of 1 to n numbers denoting a valid shuffling of these shoes where the ith student gets the shoes of the pith student, for example, where pi is not equal to I. You can of course output -1 if a valid shuffling does not exist. Alright, so let us generalize this problem quickly. You have been given a variable n and you have been given an array S. This S array is non-decreasing or basically increasing in order. Let's just take, let's say 5 numbers. Let's say S1, S2, S3, S4, S5. That means n over here is 5. Now what does S denote? S denotes the size of shoes worn by 5 students. S1 is for student 1, S2 is for student 2, S3 is for student 3, S4 is for student 4 and S5 is for student 5. Now you're looking to shuffle these shoes. An array P, which is a permutation of, in this case, n numbers, that is 5. So permutation basically means that all the numbers from 1 to 5 come in it and they come exactly once. Right now, this permutation in this question's context will represent which student gets which shoe. So very basically, you can say that right now the permutation is 1, 2, 3, 4, 5 as it is, because that means that the first shoe is with the first student, second shoe is with the second student, and so on. Fifth shoe is with the fifth student. But I want to change this permutation. The condition is I want to shuffle these shoes among the students such that every student gets a shoe which is not of their own, but rather a shoe which is somebody else's, and the shoe that they get is greater than equal to their size. This is again a very commonsensical point. In real life also, you would not want to wear a shoe that is less than your own size. So I want to change this permutation to, let's say, some other permutation P dash, where I have these 5 numbers which satisfies the condition. For example, if I say P dash as a correct shuffling is, let's say 3, 4, 5, 1, 2. If this is the correct permutation, then I'm arguing that if the first guy is getting the shoes of the third guy over here, then that means that S3 must have been greater than equal to S1. Only then the first guy can get the shoes of the third guy. Over here, if I'm saying 4 is to be placed at this location, that means I'm arguing second guy gets the shoes of the fourth guy, which means S4 should be greater than equal to S2. If I'm saying third guy gets the shoes of the fifth guy, that means S5 should be greater than equal to S3, and so on, so on, so on. So if this answer is correct, these conditions should satisfy. All right, I hope the problem makes sense. Let's quickly jump to the first test case and see what is going to be the answer if I have some values. So first test case says that n is 5. The shoe sizes are all 1, 1, 1, 1, 1. And the initial permutation that I have right now is 1, 2, 3, 4, 5. That means the first guy has the first shoe, second guy has the second shoe, third guy has the third shoe, fourth guy has the fourth shoe, and so on. Now a correct permutation according to me, which I can print actually, is 5, 1, 2, 3, 4. That means I am saying that the first guy will get the fifth person's shoe. The second guy will get the first person's shoes. The third guy will get the second person's shoes, and so on. So I'm making sure nobody gets their own shoe initially. See, all of these values don't match. I'm changing everybody's shoe. But added to that, one more thing you can cross-verify is if I'm saying that the first person gets the fifth guy's shoe, then the fifth shoe's size, that is 1, is greater than equal to the first guy's shoes. That was his original shoes. That is 1 again. So 1 is of course greater than equal to 1, which is correct. That means this works. Similarly, this works, this works, this works, and this works. So this P dash permutation is actually one of the correct answers. If I print this, then I know I have shuffled the shoes among the students in the correct manner. Let's actually take one more case over here. I have taken 8 shoes. The sizes are 2, 2, 3, 3, 3, 4, 4, 4. And now the initial permutation is first guy gets first shoe, second guy gets second shoe, and so on. Now an answer according to me, which is correct, is actually this: 2, 1, 5, 3, 4, 8, 6, 7. Now first verify, nobody is getting their own shoes anymore, right? They're getting somebody else's shoes, so that is right. And the first guy is getting second person's shoe. Then see, the first guy's shoe size was 2. The second person's shoe is having a size of 2. So is 2 greater than equal to 2? Yes, it is. So is this correct? It is. Similarly, this is correct. Yes. Over here, see, if I'm saying that the third person gets the fifth guy's shoes, then original size was 3, new size is 3. 3 is greater than equal to 3. Yes, this works out. So this is correct. This is correct. Similarly, this is also correct, and so on, so on. So this is a right answer. Pause the video and I think you will understand why is this correct. Let's take one more case also. I have said that n is equal to 4. I have the shoe sizes as 1, 2, 5, 7. Initial permutation is 1, 2, 3, 4. But over here, I think I actually cannot make any new permutation p dash. So answer according to me is -1. You can pause the video and you can try to do that and see if the condition checks out. You will actually find that you violate the condition. Hence, you will not be able to create an answer for this. That is -1. So before we start, we need expected time complexity. Now test is saying that 1 second is allowed. So that is 10 power 8 order. Inside that I have this test case variable, but it is written that sum of n over all test cases don't exceed 10 power 5 limit. So I don't need to worry about every test case. Rather, I can work with 10 power 5 order compared with directly 1 second. That is this n value. So I can say that if one test allows me 10 raised to 8 operations and n is given in 10 raised to 5 order, then I can work with a solution that is linear. I can also work with something like n log n. I can also work with n square root n. But if I go in the square order of n square, that is a problem. All right. So from here, things are pretty bad for me. Up to constant time limit, everything is great. So solutions like this is promoted. And solutions like these don't work out for me. This is expected time complexity, which is now helpful because I have a rough idea that I'm looking for a linear solution or a little higher than that only. Don't go in n square order. Great. Let us start with the problem. So I have a very important claim or argument over here, which actually makes up our answer. Argument according to me is, if any shoe size SI is unique, a valid shoe shuffling does not exist. What does this mean? This means that if any number has frequency 1 in the S array, then a valid shoe shuffling will not exist. Let's actually see why is this true. Let's take the very extreme case. Let's say S looks like 1, 3, 5, and 10. Now let us start with the first guy. The first guy wants a shoe that is greater than equal to his own. So the value 1 or the first guy over here having the value 1 can take 3, 5 or 10. So let's be very greedy over here and let's just give this guy the just next greater shoe size. So let's say that this shoe with 3 size goes to the first person. Now the same problem rises for the guy who is second. He has the shoe size 3. He wants something larger. So let's say he takes the next person's shoe, that is 5. Next time 5 says, okay, I want even better than me. So let's say 10 goes to 5. And now it's a problem. See that 10 also wants somebody who gives him shoes that is greater than equal to their size. But the only shoe that is left which is not allotted as of now is the shoe of one size which is lesser than 10. So this guy is now grumpy. He doesn't get any shoe. That means that if I had an all unique array, I actually ran into a problem. I actually ran into a -1 case where I said no valid shoe shuffling existed. Now let's try to make sure that this problem doesn't occur. Maybe let's say that if this 10 guy is not getting any other shoe which is greater than equal to their own size, let's actually create a copy of 10 and let's assume that there was one more guy who had a 10 size shoe. Now what I can do is I can say that, okay, these two people that is having the same 10-10 size, they can exchange their own shoes. So I can do something like this. Let's say this 10 goes to over here and this 10 goes to over here. So now the problem that I had for the guy who had 10 size is now done because he is getting somebody else's shoes which is greater than equal to their size. It is exactly equal to their size rather. And the other guy is also getting somebody else's size. So this part is done and dusted. But now the same problem rises with 5. 5 has no other shoe to take now. 5 cannot take 1 because 1 is unallotted but 1 is lesser than 5. So that means similarly how I resolved 10's problem, I can try to resolve 5's problem and give him another copy of 5, assuming that there is one more guy, let's say, who has a 5 shoe. He takes the other person's shoe and that person takes his own shoe. Similarly, the problem now rises with 3. So I can do a copy of 3 and they take each other's shoe. And now for 1, I simply create one more copy like same order and 1 takes this guy's and this one takes this guy's. And now don't you think I have actually created a valid shuffling? I have. Now see this simulation that happened. Every time if there was one guy who was having a unique size, that guy was not able to get anybody else's shoe which satisfied the condition. So for that, I had to create a copy of that person, which meant that eventually I landed up with an array which has no particular value, which is all unique. And this is why my initial claim was that if any value is unique, then that's a problem. In that case, a valid shoe shuffling will not exist. And this is what I showed you over here, which means that a valid shuffling is possible of this sense if every shoe size has more than one copy or has more than one frequency. And in that scenario, I can create a cyclic rotation. I can create a cyclic rotation in the segment of shoes which is all same, and everybody can get each other's shoe nicely, overall making my valid shoe shuffling correct. What does this mean? Let's imagine this. Let's say that S, now I'll talk in variables, was looking something like this. Let's say AA, BBB, CCCC, DD, EEE, something like this. These are the number of shoes. I have denoted their sizes by random names, A, B, C, D. These are the shoes. And you can see that every shoe size has individually greater than one frequency. So I know this will create a valid shuffling for me. But how will that look like? Let's say I'll talk about this segment of all A's. I can create a cyclic right shift. That means this A gets the previous guy's shoes, and this A cyclically right means since there is no right of A, it gets cyclic back to the end guy in this segment. That is, this A gets, you can say the first A gets the last A shoe. Now this is going to be even better when we expand the size. Let's talk about this segment, BBB. Over here, I'll say the last B gets the second last gets the first, and the first gets the last. This is the cyclic thing. Similarly, over here, C for this C for this C, this C for this C, and the first C for last C back, a cyclic right rotation. This D for this D, the D back over here, this E for this E for this, and back over here. Which means that if the initial permutation looked like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14, the new answer would have been P dash something like identify this segment 1 to 2, cyclic rotate, 2 and 1. Identify this segment 3, 4, 5, cyclic rotate, 4, 5, 3. Identify this segment 6, 7, 8, 9, cyclic rotate, 7, 8, 9, and then 6. This segment cyclic rotate 11 and then 10. This segment cyclic rotate, this becomes 13, 14, and 12. And this is a correct permutation indeed, because nobody is getting their own shoes. See, every value is different if you compare to the initial permutation, but they are also getting a new shoe which is equal to their size, and we wanted greater than equal to. So yes, it satisfies the condition for us. All right. So very, very clever problem, I should say. I hope the claim now makes sense. If any valid shoe shuffling has to exist, no value can be all unique. You need at least 2 copies of every shoe size so that they can shoe shuffle amongst each other. Now let us see the test cases once more and see how did that help us. See, even for the last case, it was very easy to now identify -1, because in this case, you can see 3 had unique value, even 6 was unique, 8 was unique. So we had at least one guy which was unique. I knew this was not valid, so I would have printed -1. But over here in the first case, the only shoe size that was there is 1, and it had more than one copy. It had 5 copies indeed. So I could have identified this whole 5 segment, and I would have cyclically rotated in that 5 segment to present a neat answer, which would have been correct. So my answer of 1, 2, 3, 4, 5 could have changed to simply 2, 3, 4, 5, 1. And this would have worked for me. The problem has boiled down to you identifying some segments of all equal values and cyclically rotating in that segment by one shift. That's all. If you're able to implement this, this problem is solved. All right. Now let us talk a little bit about implementation. How do we do this? So for the beginners out there, I'll give you a very simple idea. First of all, you need to identify the -1 check. To identify the -1 check, it's basically simple. Just figure out the frequency map of the whole you can say S vector, frequency map of the S vector. And if you find that any guy has one frequency, you return a -1. So this is handled. Else you go in the main solution part. Now in the solution part, you're looking to first identify a segment and then rotate in it. Now for that, we can take a 2-pointer approach. 2-pointer approach. Again, this can be replaced by various different implementations. It's all up to you. I'm giving you one of the easiest ones. 2-pointer approach will take 2 pointers L and R. You can start both of them with 0, and you can keep on moving the R pointer to the right till a segment of same values has been covered, And as soon as there is a disparity, a segment is changing or you're moving to a different segment, the segment marked by L and R can be rotated. For that, there is a very neat STL function called as rotate, which will look something like this. It will take the begin iterator, the middle iterator, and the end iterator. Begin iterator means where do you want to start your rotation from? So I would want to start from something like this. The piece permutation dot begin plus L. Why L? Because L can vary, right? L is right now 0, then it might shift to the new segment start, then it might shift to the other segment start and so on. So from the begin iterator, that is the first place in the main array, plus L, comma, I want a right cyclic rotation by 1. So I'll write it like this, p dot begin plus L plus 1. So p dot begin plus L means in the start location, plus 1 means you are looking that the first element goes back cyclic to the right and everything shifts 1, 1, 1, 1 on the left. And then the last thing is p dot begin plus R. You want this to happen from p dot begin plus R. So p dot begin plus L and p dot begin plus R becomes the start and the end of that segment, and p dot begin plus L plus 1 tells me that I want a cyclic right shift. This is again syntaxal part. You can pause the video and you can try this out on your own. You might be able to understand the working of rotate function very easily. This is a very popular STL function that we are going to use. Alright, now this is going to have a time complexity of O of n order, which is going to be fine with us because when I discuss the code piece with you, you will actually understand this is absolutely going to work fine and not give us a TLE. Alright, so this is the 2-pointer approach that I'm going to use. So for all the beginners out there, note this, 2 pointers is a very, very important concept, and this becomes a classic problem for that. Alright, so greedy plus 2-pointer is sort of a tag here. Great, so let us move on to our main code and see this in running. Alright, what will I do over here? I am going to first of all have the input t, then n, then I have the sizes vector. All right. Now I create a frequency map. After have done that, I have a flag variable which is 0. I go inside every frequency. If I dot second, that is the frequency's value, is 1, then I know flag becomes 1 and I break. Now if flag is 1, that means I got one value which is unique. I don't want that. Everything should not be unique. So I'll print a -1 and I'll continue. That means this test case has been handled and I want to move forward. But if the flag is not 1, now is when I want to actually figure out that valid shoe shuffling. For that, I first have this students vector, which is actually the p vector, which is the initial permutation you have. Initial permutation is simple. 1 to n, directly numbers are there. So students of I becomes I plus 1, I being from 0. So I plus 1 is 1, 2, 3, 4, so on till n. This is the initial vector done and dusted. Now I will cyclically rotate segments in this vector. So I have the 2-pointer L and R, while R is less than n. Now if sizes of L is equal to sizes of R, which means if you're standing over here, these are L and R. Now R expands, R moves forward. Okay, the same size, same size, same size, same size. So I'm in this segment that has all same shoe sizes. And until it is true, I move on and on. But as soon as it becomes false, I go in the else block and I rotate that much segment. So I rotate the segment from student begin plus L to student begin plus R. And I want a cyclic right rotation. So this becomes student begin plus L plus 1. And then L becomes equal to R. If you understand with the hand movement, basically L and R, if are over here, R moves, and then comes to a place where a segment ends. Then this hand, this L has to go again back to this new R. And then this continues again go forward, continues again forward. So this is like the 2-pointer approach where L catches up with R. Now, when I come out of this while loop, I know that I have crossed the limit of the whole array. So I will run this same rotate function once more, because what can happen is that maybe all the elements in the array were same. So you just had one segment of same values. You would want to rotate it at the very end because you would never have gone in the else block. So this is done and dusted, and then I simply print all the values in the students array, and that would be a valid shoe shuffling. All right, let's run this on some cases. I actually showed you the first case done and dusted. See, you are actually printing the answer as 2, 3, 4, 5, and then 1. That is valid. And I took a similar case over here, that is 2, 2, 3, 3, 4, 4, 4, 5, 5, 5. I had 10 shoes. Let's see what is getting the answer. See, the first 2 shoes have the same segment. So you have the initial value as 1, 2, but now it gets cycled. So 2, 1. This is 3, 3. That was actually 3, 4. Cyclic rotate, 4, 3. This was 5, 6, 7. Cyclic rotate, 6, 7, 5. Similarly, this was 8, 9, 10. Now becomes 9, 10, 8. All right. Now, what is the time complexity for this? Let's see. So you have an n loop over here to take the sizes input. Now I'm using a simple map, not an unordered map. So they have this extra log n factor to insert and find. So this can be n and this can be log n. So basically that gives me n log n for the creation. Pretty much this is covered. And then we have the loop of student creation. So this is n order. And then this while loop is actually n order, but inside this rotate function is also called. Now you might think that this is n into n because the rotate function is inside a n order loop, but the two pointers are working like this. Basically, if r is expanding, you stop at a location and then you rotate that much segment. So that is n plus n, not n into n. That is why this actual while loop is 2 into n and not exactly n square. Now 2 into n can be written as n only because you know that 2 is like almost a constant factor. That is why the two pointer approach works in n only. And hence my overall time complexity comes out to be n log n because that was the better factor over here. Now I could have avoided that by using an unordered map also, but we discussed in the expected time complexity, even a linear solution or even a little higher, that is n log n, all will work. So it's totally up to you. For this solution, it is n log n. N log n will mean you have something like 10 raised to 5 into log base 2 of 10 raised to 5, log base 2 of 10 raised to 5. Alright, that lands me a solution with 6 order. Alright, and what about space complexity? It is only O of n, that is coming from the vector also and the map also, that is pretty much 10 power 5 order only. Alright, so I hope the problem is clear. Greedy plus 2 pointer was what I used in this. Pause the video and dry run this whole thing out on your own. See L and R, see how they're increasing. If you are able to imagine this, I hope that helps and you will actually understand this implementation. Again, if you have a different implementation, that's also fine. The crude idea should remain same. Great. So that is all that is there in this problem. I hope you like it. Thank you for watching.